Hello. In this video, I'm going to solve a few problems with turning cars. There's some interesting physics here, and the problem solving is a little bit tricky, so I want to work through a couple of problems. The first one is here. So there's a car turning right at a stop sign, just a normal sort of 90-degree turn at an intersection maybe. And we have a couple of parameters specified. So it's turning in a quarter circle to turn right, and the radius of the circle that it's moving on is 10 meters. Car's mass is 1,000 kilograms. If the coefficient of static friction is 0.81 between the wheels and the street, find the maximum speed that the car can turn with before skidding out. Okay, so what is going on? How does a car turn? Well, one way to think about what's happening when a car turns is that we know for sure that there has to be some sort of centripetal acceleration towards the center of the circle that the car is moving on, if it's moving in a circular arc. And so there has to be some force that supplies that acceleration towards the center of the circle. And that force is going to come from the tires. It's the static friction of the tires which enable the car to turn in this way without continuing in a straight line, because that's the only point of contact between the street and the car. There's really nothing else that could influence the car's motion to make it turn on the street. So if I look at a couple of pictures that I drew here, a couple of diagrams. So this one on the left is looking at the back of the car, let's say, as it's driving. And this one's kind of looking top down. So let me draw the free body diagram of both of these. So on the left here, I've got gravity. Let me fix that. Gravity going down. There's a normal force from the street going up. And then there's some static frictional force that'll point towards the center of the circle. And that's the force that enables the car to turn, has to be. And we know it has to point in that direction because if there was no static frictional force, the car would just continue to move in a straight line. If we look at this other diagram on the right, the one that's top down, that static frictional force points this way towards the center of the circle that the car is moving on. I won't draw the normal force and gravity on this picture because they're going into and out of the page, which isn't super important. But you can see if the car starts in this position right here, static friction is going to point this way towards the center of the circle. That's what enables the velocity to start bending or changing directions over time. If there was no static friction, then the car is just going to keep going in the same direction forever and will never be able to turn. That's what happens if you try to drive a car on ice, for example. If there's no friction or there's little friction between the tires and the ground, then you can't really maneuver the car. You need that static friction to help you. All right, so the question is here, what's the maximum speed that the car can turn at before it skids out? So skidding out would be sort of flying off the turn. That is, skidding out would be flying off the turn. So that is, if the car is going this way, not being able to actually turn on the circular arc. So the car tries to turn, but really just kind of maintains its velocity or doesn't turn very much and ends up sort of riding to the high side of the road and maybe riding off the road. So let's think about this. So the condition that we have to meet here is that in order to be on a circular path, the condition to meet is that the acceleration towards the center of the circle, which I'll denote A sub c for maybe centripetal acceleration or center acceleration, has to be v squared over r. That has to be true. So let's apply Newton's second law here. So if we look at our free body diagram here on the left, let's establish a coordinate system like this. So I've got positive y up, positive x in. And at any given moment on this circle, we need n minus mg, that's the net force up and down. That's going to be equal to 0 because the car is not accelerating up or down off the street or into the street. So immediately we know that the normal force is equal to the weight in this case. And this is the y direction. In the x direction, there's only one force. There's the force of static friction. And that force of static friction better be equal to MAC, because we need that centripetal acceleration to turn the car. And so this has to be equal to mv squared over r for whatever velocity we're at. Okay, so we want to find the maximum speed that the car can turn with it before skidding out. That means that we're looking for the largest force we can generate here, because the larger the force we can generate here, the larger the velocity can be before we skid out. And you can see that kind of directly. If Fs is bigger, radius is a constant, mass is a constant, V can get bigger. It won't get bigger linearly with the maximum force that we can supply, but it'll get bigger too. So we're really looking for the maximum V, which means that we're going to plug in the maximum value of the static friction we can have. So the maximum value of the static friction will be mu s times n, and that's going to be equal to mv squared over r. But n we already said is mg. So we can say that, or I guess I can put an equality here. This is equal to mu s mg. And so if I can cancel the m's here, and I can solve directly for v. So v will be now a square root of mu s g r. And if I plug in my values, you'll notice that they're actually kind of nice values, because it's 10 meters. I'll take g to be 10 meters per second squared, and mu is 0.81. So this is actually the square root of 81. And so we end up with v is equal to 9 meters per second if we plug in the values. How big is 9 meters per second? That's about 20 miles per hour. So that seems sensible. If you try to take a kind of a sharp right turn at 20 miles an hour, that's going to feel hard to do. Okay, so that's the first problem. Let me load up the second problem here. Okay, so here's the second problem. A similar problem, but different in an important way. So another 1,000 kilogram car. There's a banked freeway on-ramp. So you can see that the on-ramp is banked at 20 degrees above horizontal. And there's a circular loop formed by this on-ramp with a radius of 50 meters. So if we looked at the top down again, we'd have some sort of loop like this, and the car would be moving on the loop again in some sort of circular path. And the radius of that path would be 50 meters here. If the coefficient of static friction is 0.7, can the car safely drive on the curve at 30 meters per second? So this is another question about how much static friction we have, how fast can the car go, but it's trickier because of this bank. So let's see how. So if we were going to draw a free body diagram here, we still have gravity pulling down on the car, straight down. But now the normal force tilts, right? So normal force isn't going to be the weight anymore for sure. There's also static friction. And so if we assume that the car is going pretty fast and is getting close to as fast as it can go, what the car would normally want to do is, if there was no static friction, then the car would just kind of maintain its velocity, right? And end up driving off of the bank. So the static friction, as the car is turning and wants to stay on this dashed line that I drew here. So the static friction has to be acting to pull the car inwards in this case, if the car is going fast enough where we're worried about it driving off the bank. So the static friction points inwards, but static friction always points along the incline here. So that points down, actually. It doesn't point exactly towards the center. But it's worth noting that if our circle is sort of in a horizontal plane, like if the car isn't changing its elevation, then the circle we're on is still sort of horizontal. It's not vertical in any way, which means that the center of the circle is in this direction from the car. And I'll denote that to say that this is the direction of the centripetal acceleration. which is a little bit non-intuitive. If the direction of the acceleration was this way, that would say we're on a circle that moves up and down too. So we'd say the center of the circle was over here somewhere, and the car would be revolving around that point, which is not true, because that would put the car sort of way down here at some point, if that makes sense. But the center of the circle is, let's say, over here, and the car it always occupies this plane around that circle. So then centripetal acceleration pulls directly horizontally here. And for that reason, I'm going to choose a coordinate system that might seem a little bit non-intuitive at first, which is just xy like this. In many other problems we've had with inclines, we've chosen a coordinate system something like this, where you take x down the incline and y normal to the incline. But in this case, it makes more sense, or it's more convenient to choose a coordinate system like I have here, because the acceleration is only in the x direction in that coordinate system. And that's why we're choosing it that way. So we're going to ask, if the car is driving at 30 meters per second, how much frictional force do we need to make that happen? And is that more or less than the maximum amount of frictional force that we can generate here? Remembering, same as in the last problem, that the maximum static frictional force will be mu s times n. Okay, so let's break this down. So we're gonna work with Newton's second law again. I'll draw some triangles. You can convince yourself that this angle is 20 and this angle is 20, because we're going to have to break these forces into components. So if I work with the y direction first, the y direction, the net force in the y direction is n sine 20 minus fs. Oh, excuse me. Not n sine 20, n cos 20, excuse me, my mistake. N cos 20 minus fs sine 20 minus mg. That's all going to be equal to 0 because we're moving in this horizontal circular path. So the car is not accelerating up or down here. And if I take the x direction, there are two forces in the x direction, or two components of forces. So that's n sine 20 plus fs cos 20. And that's going to be equal to the mass of the car times that centripetal acceleration. And we're on a circular path again, so that centripetal acceleration has to be v squared over r again. So that's always our condition if we're on some sort of circular arc. Okay, so now what we want to do is we want to solve for how big static friction is. And can we do that? Yeah, because there are two unknowns in these equations. The normal force is unknown and static friction is unknown. Everything else we know. We're given a velocity, we're given a radius, so we can calculate the centripetal acceleration. We're given a mass, we know that. The only things we don't know are n and static frictional force. So we're going to solve for the normal force, the static frictional force, and then we'll compare that static frictional force to the maximum value of the static friction and see where we are. Okay, so let's start by solving for Fs, let's say, in terms of n. So if I take this first equation, then that says that if I move stuff around a little bit, then n cos 20 minus mg over sine 20 is Fs. And you can convince yourself that's right. All I did was move static friction, that term over to the other side and divide by sine 20. That's all I did. All right, so now I'm going to take that expression here and plug that in for Fs in this equation and solve for n. That's what I'm doing. So I'm going to take that equation. So I've got n sine 20 plus n cos 20 minus mg over sine 20 times cosine 20 is equal to MAC, which is some number. I'll just leave it as AC for now. All right, and now we can group terms and try to solve for stuff. So we've got n times sine 20 plus, and if you look at this, this is a cosine times a cosine over a sine. So I can write that in a lot of different ways. I guess I'll write that as cosine squared theta over sine theta, or sine 20, I guess I'm writing, huh? So I'm plugging the angle, cosine squared 20 over sine 20. And then if I group terms on the other side, MAC plus mg cos 20 over sine 20. And now I can divide by this thing and solve for n. Let me do that. So if I do that, I won't work through all the algebra, but I'll just end up writing a value here. And the normal force is equal to 1,5,5,5,3 newtons about. Okay, that's the normal force. So now we can solve for the frictional force that we actually have if the car is going 30 meters per second by plugging back in here. So the static frictional force will just be that expression with n plugged in. So let me scroll down a little bit and I can do that. So Fs, based on that n, Fs is equal to this expression. And now everything in there is known. So if we plug in n there, we get 13493 newtons. And the reason why I'm writing out newtons is because we also have normal force denoted as n. So just to not have n equals something times n, to make it a little more clear. Okay, so then the question is it possible to generate this much frictional force? And the way we answer that question is by comparing this value to the maximum amount of static friction that we can actually have given this normal force. All right, so let's see. So the maximum frictional force we can have is equal to mu s times n. Mu s was 0.7, and n is this value that we calculated here, if we're actually achieving the circular path. And if we calculate that out, we get 10887 newtons, I think. Okay, so comparing these values, the maximum static frictional force is less than the static frictional force we would need to make this turn. So if we try to drive on this curve at 30 meters per second, we are going to fly off the bank, and that is bad because we wouldn't have enough static friction to keep us, to give us enough acceleration to keep us on a circular path. So our car is going to drift outwards relative to that circle that we want to be on, and we're going to fly off the bank. So that's bad. So we can't drive at 30 meters per second on this bank. Another question we could ask is, what's the maximum speed that we can drive at? And in that case, we want to plug in the maximum value for the static friction here. So that would be known. But what wouldn't be known is the actual value of the acceleration here, and more specifically, the value of the velocity in that acceleration. That's a slightly modified version of this problem that we could try. So yeah, I hope that these problems helped thinking through how centripetal acceleration works in this context, and I'll see you soon. Okay, bye.